let's solve this interesting geometry algebra problem together. And I want you to stay with me until the very end because the final answer turns out to be a beautiful mathematical result. If you enjoy these step-by-step explanations, don't forget to like this video, subscribe to the channel, and leave your answer in the comments before we reach the final step. We are given a right triangle whose three side lengths are a squared, and a cubed, and our goal is to find the value of a. Now let's begin by identifying the sides correctly. Since this is a right triangle, the longest side must be the hypotenuse. So a cubed is the hypotenuse, a is the base, and a squared is the perpendicular. Because this is a right triangle, we can apply the Pythagorean Theorem, which tells us that the hypotenuse whole squared equals the base whole squared plus the perpendicular whole squared. Now, let's substitute the given side lengths into this formula. The hypotenuse is a cubed, so we write the quantity a cubed whole squared equals the quantity a whole squared plus the quantity a squared whole squared. Now let's simplify each term carefully using the exponent rule, which says that when a power is raised to another power, we multiply the exponents. So a cubed whole squared becomes a to the power 6. A whole squared remains a squared, and a squared whole squared becomes a to the power 4. Therefore, our equation becomes a to the power 6 equals a squared, plus a to the power 4. Now let's move every term to the left-hand side so that the equation equals 0. This gives us a to the power 6 minus a to the power 4 minus a squared equals 0. Notice that every term contains a squared, so we can factor out the common factor, a squared. After taking a squared common, we get a squared, multiplied by the quantity, a to the power 4 minus a squared minus 1 equals 0. Since the product of two expressions equals 0, at least one of them must be 0. This gives us two possible cases. The first case is a squared equals 0. But if a squared equals 0, then one of these sides of the triangle has 0 length, and that is impossible because every side of a triangle must have a positive length. So, we reject this case completely. Now let's continue with the second case, which is a to the power 4 minus a squared minus 1 equals 0. This equation looks difficult, but notice something interesting. We have a to the power 4, which is simply a squared whole squared. That suggests making a substitution. Let capital A equal a squared. This changes our equation into capital A squared minus capital A minus 1 equals 0, which is now a standard quadratic equation. To solve it, we use the quadratic formula. The quadratic formula tells us that capital A equals minus b plus or minus the square root of b squared minus 4 multiplied by a multiplied by c, all divided by 2 multiplied by a. Here, the coefficients are a equals 1, b equals minus 1, and c equals minus 1. Now substitute these values into the formula. We get capital A equals 1 plus or minus the square root of 1 plus 4, all divided by 2. Inside the square root, 1 plus 4 becomes 5. So the equation simplifies to capital A equals the quantity 1 plus or minus square root of 5 divided by 2. This gives us two possible values. The first value is the quantity 1 plus square root of 5 divided by 2, and the second value is the quantity 1 minus square root of 5 divided by 2. Now remember, Our substitution. Capital A actually represents a squared. So we substitute back and obtain a squared equals the quantity 1 plus square root of 5 divided by 2, or a squared equals the quantity 1 minus square root of 5 divided by 2. Now, let's think carefully about the second value. Since square root of 5 is greater than 1 minus square root of 5 is negative, which means the entire fraction is negative. But a squared can never be negative because the square of a real number is always non-negative. Also, a squared represents the length of a side of the triangle, and side lengths cannot be negative. Therefore, we reject this second solution. That leaves us with a squared equals the quantity 1 plus square root of 5 divided by 2. Finally, we take the positive square root of both sides because side lengths are positive. This gives us a equals the square root of the quantity 1 plus square root of 5 divided by 2. And that is the only valid value of a for this triangle. If you reach this point, congratulations, because this problem combined geometry, exponents, factorization, substitution, and the quadratic formula all in one elegant solution. If you found the explanation helpful, make sure to like the video, subscribe for more challenging mathematics problems, and comment below whether you spotted the substitution before I introduced it. I'll see you in the next one.